Okay, and for our final speech for this session, we have Justin Cheng from University of Minnesota. Field was material science and engineering. Advisor is here. Nathan Mara is here. Practicum was done for 2 years, both at Sandia National Laboratories in 2021 and 2022. And just making sure the title, extreme mechanical stability at the nanoscale through 3D interfaces.
Yeah, thank you very much. Yeah, so thank you very much for the kind introduction. Yeah, before I'd like to start, I'd like to thank NNSA for funding me to be able to do this work. So yeah, I guess I'll just start right away. So why do we care about my research? Why do I care about my research? The reason why we study metals, which is what my research focuses on, is because in today's modern world, there are a lot of technological demand for high-strength alloys. So there's a lot of different applications for these alloys. So for example, in the field of automotives, they're always chasing higher and higher mileage, so fuel efficiency. And one great way to do that is to replace heavy components in a car with more lightweight, higher specific strength materials, so materials that have both high strength and relatively low density. One other application for high-strength alloys is in the aerospace industry. So if you look here, this is a cutaway of a aircraft engine, which a lot of us flew here on. And you see in the middle section here, there's a lot of these leaf-shaped parts, and each one of these is a turbine blade. So each of these turbine blades is made up of a core of nickel-based superalloy. And the reason why you use this material is it can maintain mechanical stability under extreme temperatures, so very high temperatures of 1500 degrees C. And the list goes on and on and on. Maybe what might be more relevant to this community is you also like high-strength alloys for use in nuclear power plants, because those materials have to withstand high corrosion, high radiation, mechanical stress, and yeah, oxidation. So how do we define mechanical stability? Well, what we would like is we like metals with a combination of a high yield strength and high ductility. So what do I mean by this? I'd like to go back to the basics for those of us who aren't complete metalheads like me. So this is a very, very brief introduction to solid mechanics. When we measure mechanical properties of a material, we like to use one of the gold standards of mechanical testing, which is a tensile test. So it's a very simple test. You take a specimen with a predefined geometry, and you pull on it until it breaks. And then during this test, you continuously measure load and displacement. And this allows you to calculate what we call stress and strain. So to do that, you have to know the geometry of your specimen's gauge length. And the gauge length is just the part of the specimen that deforms during the test. It has a gauge length L and a cross-sectional area A. And when you pull on it, then the geometry changes, the length changes, the cross-sectional area changes. And this allows you to calculate stress and strain. So stress is how hard are you pulling or pushing on something. Strain is how far do you pull or push on it. So one common definition of it is the engineering stress and strain. The engineering stress is sigma equals the force divided by the initial cross-sectional area. And the strain would be epsilon, which is the change in length divided by the initial gauge length. You can also use instantaneous values for this, true stress and strain, but we really only need to understand engineering for this talk. So when you calculate stress and strain, it gives you what's called the stress-strain curve of the material. We plot sigma versus epsilon, and then you find that the curve has two very distinct portions. The initial loading segment of the curve is linear, and it's what we call the elastic portion of the curve. So if you pull on the material and let go, it returns to its original shape, like a spring. But if you go past that point, then you start plastically deforming the material, and that means any additional deformation you give to the material is permanent. So you've changed the shape of the material permanently. The point that separates these two regions on the curve is called the yield point. When we get the stress at the yield point, we get the yield stress, and that is one of our main metrics for mechanical performance. And then we can also take what's called the ultimate tensile stress on this curve. That's just the maximum, where you have the maximum tensile stress. And if you take the difference in strain between these 2 points, you get what's called the ductility of the material. So how far can you pull the material before it breaks? And the reason why we take between these 2 points is because past this point, you start getting what's called necking. That's a form of plastic instability where strain starts concentrating in a small portion of your sample, and that's when your sample starts to break or fail. So I'd like to thank Sandra for covering a lot of this so I can go quicker through it. But yeah, in most cases of metallic deformation, by most cases I mean quasi-static strain rates and room temperature. Deformation is mediated by dislocation motion. So here's a cartoon of a crystal structure. Most metals are crystalline in nature. And a common dislocation that we'd like to discuss is the edge dislocation, because it's easy to draw. It's defined by an extra half plane inserted into this crystal lattice. And we also can define what's called the Burgers vector associated with this dislocation. So to define this Burgers vector, we have to draw a closed circuit on an undefected region of the crystal. We can make this closed circuit. And then if you try to draw this loop around the dislocation core, you end up a little bit short if you try to draw the loop with the same perimeter. So this extra displacement is called the Burgers vector, and the Burgers vector is important because the movement of each dislocation contributes one Burgers vector's worth of deformation in the material. And then, so what really is the crux of my work is the interaction between collections of dislocations and other defects like grain boundaries in materials. So here, oh no, I do have it. Okay, this is work out of Josh Katcher's group. You can see at the top left of this TEM micrograph, there's dislocation pileups. So you can think of pileups as like traffic jams of dislocations. And it's hitting this grain boundary here. And then this is actually in situ TEM footage. So you can see as you apply strain and cause the material to deform, these dislocations are moving, and it's the movement of these dislocations that gives you your macroscopic shape change. So what this really drives home is that defects have stress fields, they have atomic structures, and these stress fields and atomic structures interact with each other to give you your macroscopic material properties. So again, we previously discussed the Hall-Petch phenomenon. So really quickly, if you have two different grains, so distinct grains in a metal are just two regions in the metal where the crystalline lattice is misoriented. You'll have what's potentially a dislocation pileup interacting with the grain boundary, and if you just assume that the grain boundary interacts with the dislocations by blocking their motion, what you find is that if you've got a single dislocation trying to cross this grain boundary, it won't be able to because the grain boundary poses an obstacle to that single dislocation. But as soon as you have multiple dislocations, you develop what's called a mechanical advantage at the dislocation pileup. So all of these dislocations in the pileup push on the lead dislocation and transmit slip across the grain boundary. So the reason why you get hardening when you decrease the grain size is because you limit the maximum allowable dislocation pileup size, decreasing its mechanical advantage, and then you don't have as favorable conditions for slip transfer across the interface. So you can kind of see this for if you compare coarse-grained and nanocrystalline pure copper. You decrease the grain size, you increase your strength, you decrease your ductility, and that kind of demonstrates what we call the strength-ductility trade-off. It's a very, very fundamental problem in alloy design, and we're always looking for ways to kind of surpass it. So you might say, okay, well, you don't get a free lunch. It's kind of hopeless if you can't get a free lunch by decreasing the grain size. But nanocrystalline materials are very, very interesting because they give you a great opportunity. They have a very high interface content compared to the bulk crystal material to tailor your interface structure to change your mechanical properties. So people have done this before in the literature. One example is to include lots of twin boundaries. So again, with pure copper, what you can do is you can put in these twins. And these twins will introduce what are called twin boundaries. They're a special type of interface. We don't have to get into specifically what they are. But if you introduce twin lamellae of average thickness 4 nanometers, what you can do is, even though you're decreasing the effective space in which you can build up dislocation pileups, you are increasing your strength and ductility. So this is a great example of how you can control interface structure to enhance mechanical performance. And so now we're coming to closer to the topic of my thesis, finally, where if you have a multi-phase material, so just a material with 2 different phases or more, you can end up with heterophase interfaces that separate your regions of different phase on top of your grain boundaries. And so that gives you another degree of freedom to change interface structure to tailor your mechanical properties. And so that brings me to the material system that I study in terms of mechanical properties. They're metallic nanolaminates, and the reason why we use them is they're very, very useful for studying fundamental physics in terms of dislocation interactions with specific interface types. So here it's, well, depending on the metals that are in your nanolaminate, you can change the types of interfaces that you have. So yeah, my nano-layered materials are made up of alternating layers of two different materials. We like to work at the nanoscale, so the layer thickness is below 100 nanometers. And the specific nanolaminate that I study is copper niobium. So the reason why we use copper niobium is, well, I'll give you two reasons now. One is that it is very well studied. It's a well-studied system in the literature. So we have a lot of previous data to work off of and compare with to use as control. And the other thing is that if you make these nanolaminates using physical vapor deposition, you get a very strong alignment between compact planes and directions between your copper and niobium. And this cuts down on the distribution of interface types that you have in your material and cuts down on the number of variables that you have to account for when you're looking at the effective interface structure on mechanical properties. And so a lot of what has been studied on the literature, this is a high-resolution TEM micrograph where you can see the different crystal structures associated with different regions of the material. A lot of these, the interfaces that have been studied are abrupt. So within the length scale of a few atomic widths, you transition abruptly from copper to niobium. So what does this do for your mechanical properties? Well, it's been found that these types of interfaces, if you have a layer thickness of 40 nanometers, you can get very, very high strengths in these materials. So the flow stress of 1.75 GPa in this example. This is higher than the rule of mixtures strength of the material. So you know that the heterophase interfaces are giving you higher strength. But what you find in micropolar compression, so the rest of this talk I'm going to talk about compression, it's the opposite of tension. Instead of pulling on material, you're pushing on it. What you find is that the uniform deformability of the material is limited by a type of plastic instability called shear banding. And that's where a region in your material starts sliding more heavily than the surrounding region. So if you cut open the micropolar after deformation, you can clearly see some regions are more heavily deformed than others. And so what we like to do is try to find ways to avoid plastic instabilities like shear localization, and we do that by changing interface structure. So really quickly, yeah, what the abrupt interfaces that were done before in the literature, we like to call 2D interfaces. And 2D interface copper niobium, we just call 2D copper niobium. What I've been working on my thesis are what are called 3D interfaces. So what we do is we extend the interface in the out-of-interface plane direction. So now the interface is taking up significant dimensionality in the out-of-interface plane direction. And these interfaces actually have crystallographic and chemical heterogeneities on the length scale of a few nanometers in all spatial dimensions. So they're 3D in multiple respects. We call these 3D interfaces. And a 3D interface containing copper niobium we call 3D copper niobium. So the way that we make this type of material is using physical vapor deposition. And during the deposition process, between depositing pure layers, we grade the deposition powers of our targets gradually. So we end up co-sputtering copper niobium at a ramped composition across the interface. And here we can see that in our work, we use the parameter h to refer to the pure layer thickness and the parameter h prime to refer to the interface thickness. And I have the shorthand for my samples h dash h prime. So if you've got 1010 copper niobium, that's your h is 10 nanometers and your h prime is also 10 nanometers. So before we talk about the mechanical properties of 3D copper niobium, we have to investigate its microstructure first, because as for all materials, your properties come from your microstructure. So if you look at a conventional magnification TEM micrograph, you can see that there's distinct diffraction contrast associated with your 3D interfaces. And if you zoom in and do high resolution TEM, you can kind of see where this distinct diffraction contrast is coming from. So here in the middle of this micrograph, there's the 3D interface, and on either side we have FCC copper and BCC niobium. And we take what are called FFTs, so fast Fourier transforms. This tells us about the local crystalline structure in the material. We find that there are crystallographic heterogeneities laterally in the interface and also through the through thickness dimension. Now there is a limitation with TEM, and that's that you are averaging out heterogeneities in the material along the electron beam direction. So we also wanted to map these 3D interfaces in all spatial dimensions. So what we did is we conducted atom probe tomography. So for those of you not in the know, atom probe tomography is a method where you take a needle-shaped specimen, you vaporize it and send the vaporized atoms through a time-of-flight mass spectrometer, and then after the TOF MS, it hits a detector, and you vaporize your specimen layer by layer. After which you can then reconstruct a 3D spatial map of your chemistry in your specimen. And then what we found, you can actually start to see the chemical heterogeneities that I was talking about. But if you make heat maps of copper concentration in the material, you can actually see, so this is an XY section of inside a 3D interface, and you can take chemical profiles along the X and Y direction, and you find out, yes, in fact, we do have chemical heterogeneities on the length scale of a few nanometers. So what does this structure do for your mechanical properties? Well, what we found is that if you just have a layer thickness of 40 nanometers and you add a 10 nanometer 3D interface into the material, what you find is that your flow stress increases, but you don't get a decrease in uniform deformability. So that's great. You're already starting to break down the strength ductility trade-off that limits the development of next generation alloys. But if you cut open a deformed pillar and then look at it using TM, you can see you still get a shear band. So shear banding is still limiting the deformability of this material. So what do? Well, we actually do use a traditional alloy development strategy. You decrease H, so if you decrease the layer thickness, you're decreasing the effective grain size of the material. And what you find here is in situ SEM micropillar compression tests of two different materials. On the left, I have 4010 copper niobium. On the right, I have 1010 copper niobium. And if you rewind these compression tests, what you find, and look for the point where you start to get gross shape change of the pillar, you find that at a lower H, you get a later onset of gross shape change. So this is suggesting that just by decreasing H, we're starting to arrest the formation of a shear band. In terms of mechanical properties, you can see that if you decrease H, you get an increase in flow stress, and you also get an increase in plastic strain to failure. So this is a complete breakdown of the strength ductility trade-off. That's great. This is, we found a new way to overcome that limitation of metals by controlling our interface structure. Now, we wanted to go a little bit deeper and understand what's happening at the atomic scale that undergirds this improvement in mechanical properties. And to do that, we first developed a kind of toy model hypothesis where at 1010 copper niobium, where your layer thickness is limited, you can only develop limited dislocation pileup sizes, and therefore, and those pileup sizes aren't big enough to drive slip across the 3D interfaces, which are posing a barrier to slip transfer. And so you start activating slip systems isotropically. However, for the 4010 case, what's happening is that you are getting significantly big dislocation pileups, and these pileups are big enough to drive slip transfer across the interface. And once you can have that, you can start driving a shear band across the entire width of the pillar, and then that's what's limiting your deformability. So we tested this hypothesis by teaming up with very talented folks at UCSB to do phase field dislocation dynamics. Thankfully, Lauren Fay is going to be presenting about that in detail tomorrow, so I don't have to go into the gore details. But basically, what phase field does for you is it allows you to simulate the collective motions of dislocations and their interactions with other defects at quasi-static strain rates. So that's a simulational capability that few other methods can achieve. And so what our phase field dislocation dynamics told us is if we plot the stress, the resolved shear stress it takes to drive slip transfer across a 3D interface, plot that as a function of 3D interface thickness and dislocation pileup size, you see these bars on the right tell you that if your dislocation pileup is small enough compared to the thickness of your 3D interface, you can significantly frustrate slip transfer, and therefore frustrate the formation of shear bands and increase the deformability of your material. So that was one big part of my thesis. I'd like to finish off with another part of my thesis that we're working into a paper right now. I don't really have much time for it, but here goes. So the loading orientation that I've been presenting this entire presentation was what we like to call normal compression. So the reason why I call it normal compression is that the loading axis is oriented perpendicular or normal to your interface planes. What you can also do is you can also do what's called 45-degree compression. You just orient your loading axis 45 degrees with respect to your interface planes. And what that allows you to do is it allows you to probe the shear response of your interfaces. So You can see for 2D interface or 2D copper niobium, if you do 45-degree compression on it, you've got a respectable ultimate compressive stress and significant plastic strain to failure, but you see hallmarks of very sharp shear instability in the pillar. Basically, you're having sliding like a deck of cards across a very limited region of the material. Now, if you add a 3D interface at a comparable layer thickness, what you find is that you increase your ultimate compressive stress, and you also increase your engineering plastic strain that you can sustain before the material ruptures. Well, the material didn't even rupture in this case, so that is very promising. So basically what this tells us is that 3D interfaces respond favorably when loaded in shear as well as compression. And they're a great way forward to enhancing mechanical properties along multiple loading orientations multiple loading orientations. So and I'd like to finish off with the TEM micrographs, because I love TEM, of these pillars. So you can see that at 15% global plastic strain, you start to see a bulge form at the top of your pillar. So you might think, okay, there might be a plastic instability. But that's not the case, because if you increase the global plastic strain to 30%, this bulge ends up taking up the entire gauge length of the pillar. The entire gauge length participates in deformation, and that is very favorable for uniform deformability. So with that, I'd like to just leave you with a few conclusions, and I really should be dedicate most of my time towards thanking my many collaborators. So the Morrow group at University of Minnesota, who helped me get here. Irene Byerling at UCSB, Suozu Xu, who is now at University of Oklahoma. They were provided the PFDD simulations for this work and were instrumental in making the conclusions that we did. John Poplowski at Oak Ridge National Lab for doing atom probe tomography for us, and Kevin Baldwin at Los Alamos National Labs for depositing the thin films needed for this work. And finally, I'd like to thank again my funding sources, the US Department of Energy Office of Science for funding this project, and the NNSA SSGF program for funding me personally. And with that, I'd like to take any questions.